In the previous video, we learned about a numerical approach to solving differential equations called Euler's method. Euler's method is based on an approximation, and so it generates only a rough version of the true solution to a differential equation. We've discussed how Euler's method can be made to work better, and we have, in our bag of tricks, one good strategy for pulling this off. The goal of this video is to give you another way of improving the match between a computed solution to a differential equation and the true one. As you'll see, the improvements will not be made by changing how we carry out the steps in a computation. Rather, they'll be made by changing the details of the steps themselves. Basically, we build a new and improved computational method by making a structural modification to Euler. You'll hopefully remember the story behind Euler. We're challenged to solve an initial value problem like this. For times t from t0 to tf. We begin our computation by dividing the time interval into a number of subintervals and use these to establish a set of discrete points in time. We then basically treat the problem as if the relevant details go unchanged between the various discrete points in time we've identified. So, if we commit to the computed solution being equal to u of t sub k minus 1 at time t sub k minus 1, then the rate of change in the solution between times t sub k minus 1 and time t sub k is given by f evaluated at the left-hand end of the subinterval. This in turn means that the computed solution at time t sub k is given by this formula. Now, the improvements to Euler that I want to describe for you arose because a clever person asked what would happen if, rather than evaluating f at the left endpoint of a subinterval, we evaluated it somewhere in the middle to capture at least some of the change that is occurring in the subinterval itself. And with that, the midpoint method was born. Here, in a bit more detail, is how it works. Step 1 is exactly the same as it was with Euler. We take the interval over which we're looking to compute a solution and divide it into capital S subintervals, each of width h. The new stuff happens in steps 2 and 3, which I'm just going to roll together here. We iterate forward in time, beginning with the initial condition, but now the recursion we use is this. Note that the capital F function that describes the rate of change in the solution is now being evaluated at the midpoint of the subinterval. This makes sense, but there is only one outstanding detail. How do we find the value of the solution at the halfway point? At this point, we only have u at time t sub k minus 1. The short answer is we have to employ an Euler half step, which actually sounds like a pretty terrible dance. What we actually do is carry out the computation we would have done for Euler's method, but instead of using h as our time step, we use h divided by 2. The end result is this: u at time t sub k minus 1 plus h divided by 2. This is the value we can plug into f to complete the iterative steps of the midpoint method. There's a lot going on here, so let's summarize all the steps of the midpoint method so we can stay organized. First, you divide the interval into capital S subintervals with right-hand endpoints t1, t2, up to and including t sub capital S. Next, beginning with the initial condition, you iterate forward in time by A, carrying out the Euler half step, then B, computing u at the start of the next subinterval using the modified recursion. Once you've computed u at t sub capital S, you can report the results of the computation. Notice that you're not reporting the results of the various half steps you've computed. Let's take this new method for a test drive with the example from the previous video. We'll look to solve this initial value problem. Now, using the midpoint method with capital S is equal to 4 subintervals, and for values of t between 0 and 2. Remember, we have an exact solution that can act as a check on how well the numerical method performs. Rather than carrying out my calculations by hand, I'll again turn to a spreadsheet. I'm dividing an interval of width 2 into 4 equal subintervals, so each subinterval is of width 0.5. This means I'm interested in times 0.5, 1, 1.5, and 2. I don't want to forget the initial condition, and so I'll put that in here right at the top. I also don't want to forget about my half steps. To calculate those, I'll need to consider what's happening at times 0.25, 0.75, 1.25, and 1.75. So now I'm ready to compute my first Euler half step. I take 2 times the initial s value and add it to 3 times the initial t value. The entire thing here gets multiplied by half the width of a subinterval, or 0.25. I then take the result and add it to the initial value of s. The result of my half step is an s value equal to 1.5, as you can see here. Moving on, I compute the value of s at time 0.5 by taking 2 times the half step value of s plus 3 times the half step value of t, then multiplying the result by the full width of the subinterval, 0.5. I add this to the initial value of s to get 2.875. Now I just repeat these basic steps until the end of the interval of interest. Then I report the data highlighted in yellow. It's ready for plotting. I've plotted the results here in the center of the screen and included results from Euler on the left for comparison. In both cases, we have s on the vertical axis and t on the horizontal. You can see that the midpoint method with capital S is equal to 4 subintervals outperforms the corresponding Euler procedure. That's the advantage of evaluating the capital F function at the midpoint coming through. We've now got a method that accounts for some of the change in the solution that occurs during any given subinterval. You might balk at my choice to compare the midpoint with capital S is equal to 4 subintervals to Euler with capital S is equal to 4 subintervals, since the former requires about 8 computations, whereas the latter only requires about 4. If that's the beef you have, then we can certainly compare the midpoint results to those of Euler with capital S is equal to 8 subintervals, and still, the midpoint method seems to do better. In advanced courses in numerical analysis, you show that what seems to be true in this example is in fact true. The midpoint method outperforms Euler in that error in Euler's method tends to 0 like the width of a subinterval, but error in the midpoint method goes to 0 more quickly, like the width of a subinterval squared. Let's now recap what we've done in this video. We described a modified numerical method for solving first-order differential equations. It's called the midpoint method. Using an example, we saw how to implement the midpoint method on a computer. Using the same example, we saw that while there is error in the solutions generated by the midpoint method, it still outperforms Euler. You should now be able to do at least 2 things. You should be able to describe the steps required to apply the midpoint method and implement these steps on a computer. You should also be able to explain what structural changes gave the midpoint method a performance advantage over Euler, and you should be able to outline why these changes make a difference. I hope you know by now that watching this video is just the first step toward mastering and understanding numerical approaches to differential equations. Make sure you do the readings and chat with your classmates. Try making up your own problems and solving them on a spreadsheet like we've done in the video. Maybe even try to devise your own numerical method. Who knows, maybe I'll be talking about you in this course 10 years from now. That'd be something worth dancing about.